Hello, and welcome back to the Maths Behind the Economics YouTube channel and to the Logs for Economics series. This is video 9 in this series, and now we're going to talk about what happens when you have division behind the log signs. Again, we will present the rule that we introduced in video 7, but now I'm also going to go into more details why the rule works. I'm going to prove it to you, and as always, we're going to look at many examples. And again, like in the previous video, I have neatly typed out for you the rules, so it is nice and easy to read. So what the rule says, if I have got some general log base, which I denote by log b, and there is a division or a fraction behind that same log base, then we can break that log out into two separate logs with a subtraction between them, but now the arguments are individually the numerator and the denominator of the previous fraction. And when it comes to the special case of the natural log, which is very often used in economics, the rule simplifies down to ln x over y is equal to ln x minus ln y. And just as in the previous example, when we looked at what happens to a log when there is a multiplication behind it, let us look at how the rule applies, what's actually happening in the rule. Well, first of all, we need to make sure that the bases are the same, because that's what the rule tells us. But also, as I already mentioned, the numerator becomes a single argument and the denominator becomes another single argument behind the same log. And now here is where the difference is from the multiplication rule. In the multiplication rule we had an addition, here now we have got a subtraction. So this is what the rule tells us, but just because somebody said this is a rule, you shouldn't believe them. You need to be able to convince yourselves and others that this is actually generally a rule. So it's always a good idea to test it with some simple examples. So let's look at what happens in the case of log base 3, 27 over 3. Is that equal to log base 3, 27 minus log base 3, 3? Well, let's look at the left-hand side. Well, the left-hand side is log base 3, 27 over 3, which if I carry out the division or simplify the fraction, we'll get down to log base 3, 9, because 27 divided by 3 gives me 9. And knowing what the logs are, I know that this is equal to 2, because 3 squared gives me back the 9. Right, after making a bit more space, now let us look at the right-hand side. What's going on in there? Well, in the right-hand side, we have got log base 327, which is equal to 3, because 3 cubed is 27, and log base 3, 3 is also on the right-hand side, which I know is equal to 1, because again, 3 to the first is equal to 3. But in contrast to the previous video, when we added these two together, now we have to subtract them. So they're going to yield 3 minus 1, which is equal to 2. Well, that's lucky for us, isn't it? Because the left-hand side cancels down to 2, and the right-hand side also cancels down to 2. Was that just pure luck, or are we onto something? Let's test another example and see whether log base 2, 16 over 8, is equal to log base 2, 16 minus log base 2, 8. Again, let us follow a similar approach and test the left-hand side and the right-hand side separately. Well, the left-hand side says log base 2, 16 over 8. Well, what does 16 over 8 cancels down to, or what is 16 divided by 8 is equal to? Is equal to 2. And this whole log expression is cancelling down to 1. Again, if you don't remember this, please look at video 5 in this series when I went into quite some details why and how this works. Now, let's move on to the right-hand side. The right-hand side gives us log base 2, 16 and log base 2, 8. What's furthermore, we're going to have to calculate the difference of them, but to be able to calculate the difference, first we need to know what these are. Well, log base 2, 16 is just 4, because 2 to the 4 is equal to 16. And log base 2/8 is equal to 3 because 2 to the 3 is equal to 8. And now the last thing, we have to subtract these two, which is going to give me 4 minus 3, which is incidentally equal to 1. So the left hand side is equal to 1 and the right hand side difference is also equal to 1. So I think after seeing a couple of examples, you start to feel the confidence that yes, this looks like it could be a rule. But like with everything in mathematics, you cannot just take it because it works in a couple of examples. You have to look at the general case and you have to prove it for the general case. So let us dig into details why this rule is true and how we can prove it. Again, make some proper space and use the correct mathematical language. Let b, because that's going to be our base, be bigger than 0 and also not equal to 1. Then next, the criteria for the arguments that x and y have to be both positive. Now again, we can use the definition of the logs with the special properties that we established in video 6, that x over y can be expressed as b to the log base b x over y. And again, x can be expressed as b to the log base x, and y can be expressed as b to the log base b y. We're going to follow a similar approach as we did in the previous video when we showed the multiplication behind the logs, but because it's division, it will be slightly different. So, first of all, I can express x over y in a slightly different way too. So, that can be equal to b to the log base bx over b to the log base by. Now, why is this any good for me? Well, this is good for me because I have got the same bases divided by one another. And if you remember the exponents very well, and this is again where I keep saying that logs depend on the exponents, so if you don't understand logs very well, you might be missing some of the properties of the exponents. So here now, we can subtract the exponents. So we can write b to the log base bx minus the log base by. If you don't remember this rule or if you have not seen it, please watch video 3 from the Exponents for Economics series. Now, what's important here for me is that I expressed x over y in two different forms. The first form is just b to the log bx over y, but the other form is b to the log bx minus log by. Because the starting expressions are exactly the same, the expressions I ended up with also have to be equal. So therefore, I can claim that b to the log bx over y have to be equal to b to the log bx minus log by. Let us make a bit more space. And again, here comes that cheeky little sentence that we haven't really covered yet, but if you keep at the series, we will eventually get there and I will show you what continuity is, what monotonity is, and then the whole picture will hopefully be much clearer. But for now, we just have to make do with this little cheeky sentence that due to the properties of the exponential function, we can conclude that log base bx over y is equal to log base bx minus log base by. And again, I haven't used a specific base, I haven't used a specific argument, so this is not an example anymore. This is a formal mathematical proof. And again, just like I emphasized in the previous video, you might feel like this is an overkill and you actually don't need it. But these, in my opinion, are one of the most valuable skills that we have to master in the world of the emerging AI and language models. because you have to be smarter than the language model and be able to decide what the language model tells you is actually true or not. Now, remind ourselves what it looked like in the special case of the natural logarithm. So that was ln of x over y equal ln of x minus ln of y. So I hope you are now ready for some practice questions. And again, let us make some more space and look at exercise 1. ln 12 plus ln 5 minus ln 6. What can I do here? Well, I can put it all into the calculator and I get an answer. That's all fine and lovely. But then again, let me just see if I can make it simpler and rewrite this whole expression using just one log sign. Well, first of all, I noticed that when I'm adding logs together, I can just replace that with one log sign and a multiple of the two arguments. Look, equalities go both ways. You can combine logarithmic additions into one log sign with the multiplication of the argument, as well as extend a log sign with multiplication into two log sign with additions. But then next, I still have got the ln of 6. So 12 times 5 is 60. So this is basically ln of 60 minus ln of 6. What else can I do? Well, I can just simplify this into one log sign where the arguments are divided. 60 over 6, and that can cancel down to just ln 10. And this is much simpler than the expression I started with. I give it to you. If you can use the calculator, you can just plug it all in and you don't have to go through all this algebra. But there is something nice about the numbers that we usually feel more comfortable with. And if you can practice these skills with the numbers, then you are more likely to recognize these manipulations when those numbers are replaced by letters, which is very common in economics. Right? Let's look at example 2. Log b x to the 5 minus log b x squared. So again, I have got two logs with the same bases and there's a subtraction between them. So I can replace this with one log sign with the same base and then just divide the two arguments. So x to the 5 over x squared. Now I can use my knowledge of exponents and I can cancel down x to the 5 over x to the squared to x cubed. Let us do that. Log base bx cubed. But the other thing I know that x cubed is just x times x times x. So this can be replaced as log bx plus log bx plus log bx. So I don't know this value because I don't know the base and I don't know the argument, but I know that I have got the same value repeated 3 times. So this is just equal to 3 times that one value, log base bx. Now listen, one way you think about it is you can just replace log bx by an apple. I have got an apple and I have got another apple and I have got another apple. I've got 3 apples. So this expression can be replaced as 3 times log bx. Right, third question. Log base a 5p over 7q. Well, I can break these out into individual logs. So I can replace this as log a 5p minus log a 7q. Remember, the fraction can be broken out into a subtraction. Now, in the numerator of the fraction, which is now the argument of the first log, is a multiplication of 5 times p, because remember, in mathematics, if there's nothing between a letter and a number, it's always multiplication. Then now I can use the first rule, the multiplication rule, and I can break this out into log a5 plus log a p. Then next, I'm going to put a bracket in here because what's going on in here is I have got a multiplication behind the second log sign, so I can break that out into an addition of logs, but the subtraction sign applies to the whole log sign, so I'm going to have to apply that to both of the terms in the addition. So that's going to have to be log a5 7 plus log a q. And I have to make sure that this is a long enough tail here so we don't mistake the a with the q. Let's close the bracket and then move on to the next line. So I still have got a negative here with a bracket. So what I need to do is apply that negative to everything into the bracket, because when I'm taking away the bracket, I'm taking away everything inside the bracket. So the first two terms don't change. That's going to be log base a5 plus log base AP, take away log base a7, and also take away log base AQ. And now what we achieved is we've been able to break out this long expression into sums and differences of individual arguments of the same log base. Again, make a bit more space and move on to question 4. ln x cubed over y to the 5th. Well, there's a fraction behind the log sign, which is the same as division. So I can replace these with subtractions. So I can write ln x cubed minus ln y to the 5th. Now, what I can do here, well, I know that x cubed is x times x times x, and I can apply the addition rule repeatedly. So I would end up here with ln x plus ln x plus ln x. Well, that's just going to give me 3 of the ln x's, so I can just replace this ln x cubed by 3 of ln x. Now, what's going on with ln y to the 5th? Well, y to the 5th is equal to y times y times y times y times y. Phew, thank God for the exponent notation. But again, I can apply the addition log rules repeatedly. So this would be ln y plus ln y plus ln y, and I have to write that down 2 more times because there are 5 of them. A little bit boring, too much writing, but nevertheless, I've got 5 times the same expression, so I can just replace this by 5 ln y. There is something nice about seeing this simpler form compared to the starting form we had in here. It just makes me calmer. Right, last example for which we again gonna need more space. So log base 5 15 minus log base 5 3 plus log base 5 10 plus log base 5 2. Wow, this is a long expression with loads of logs. Let's see what we can do. Well, the first two we could combine together into a division or a fraction, if you like. So we can rewrite the first two as log base 5 15 over 3 plus the other two can be replaced with a log multiplication, which would give us log base 5 10 times 2. I'm going to put it into a bracket because I want to make sure that we remember that both 10 and 2 have to have the log applied to. Right, let's do the basic algebra here now. So log base 5 15 over 3 gonna give me 5 plus log base 5 10 times 2 gives me 20. Okay, I still have got an addition between my log signs which have got the same base. Remember, I can't apply this rule if the bases are not the same, so they have to be the same base. So again, I've got log base, bracket open, 5 times 20. So that's going to give me log base 5 100. Okay, I can put that in the calculator now, and I can calculate one exact number if I needed to. But in most cases, you can leave your answer as it is, log 5 100. This is just a number in disguise. Remember, if you know the base and if you know the argument, if both of them are numbers, then you can calculate the value, and this is just a number in disguise. It's just a number hiding there. Right, this is the end of this video. I hope you've learned something new. I hope that you're feeling a little bit more confident at following through mathematical proofs and working with expressions and letters and numbers, which will be extremely important for your economics studies, especially if you are aiming to get high grades. In the next video, I'm going to go into the next rule, which is going to show us what to do if we have got exponents behind the log signs. Hope to see you there. Bye for now.